So the plan today is to move on, talk about Cartesian products, and do some more work with sets, and kind of move on from induction. So if you are still having some questions about induction, definitely, where Lindsay and I can help you out with that. I just want to make one announcement. Normally, my office hours on Thursdays are 10:30 to 11:30. I have to move them for tomorrow. So just for tomorrow, I'm just going to move them to 12 to 1, and I will post an announcement about that in Canvas just to let you all know. Okay, so any other questions before we get things rolling today? Okay, so I want to just kind of start by, I'm just about done grading your induction homework from last time. So I will get those up probably later today, at the latest tomorrow morning. And I would definitely encourage you to look over those comments before you hand in your next homework assignment, which is on induction again. But just a couple of things that are worth pointing out together, since I've been seeing things like this on a number of homework assignments. So this was question 3 on the last homework assignment that hopefully looks familiar. You were trying to prove this formula for the derivative of natural log to the nth power. And the claim is that this is equal to n over x times the natural log of n minus raised to the n minus 1. So right, base case would be n equals 1. And I'll just say that a lot of people are just organizing the base case with one equation. And the confusing thing for a reader about this is it's not clear to me that you're checking two different things. It looks like you're just simplifying one thing. So to me, this just looks like you were, this person was starting with this. Okay, they plugged in 1. This is not how anybody would write out the derivative for the natural log, right? It looks kind of weird to put this here. So I think the thinking here would be more like, okay, when I get that, I get 1 over x. And then this is now another side of the equation. So on the other side of the equation, we're going to plug n equals 1 into this and make sure that we also get 1 over x. So when you kind of just write it out as one string of an equation, to me, this looks like you're simplifying just the left side. And I get that the person probably has the right idea, but I shouldn't have to guess at that. So just make it abundantly clear. So here's an example of what I think would be this stated in a clearer way. So here you can see, okay, I checked this on the left side. When you take the derivative of this, you're not going to write out natural log raised to the 0, probably. You would just use the shortcut that this is 1 over x. And then on the right side, you get that this is equal when I plug n equals 1. And this makes it more clear to me. So just keep that in mind. But any questions? So I will say that overall induction, your guys are doing a really good job with induction. I do write a lot of comments on your homework, even if you write good proofs, just because I think that's the only way we all can improve no matter where you're at right now. So I'm giving you feedback just to let you know, here are some things that you might be able to improve on your proof. And don't take that as like your proof is not very good. You're probably still getting good scores on those. And so here's this proof again, and I want to just kind of go through the induction steps. So we're trying to prove this formula for the derivative of the natural log to the kth power. So here's the induction step. And so this looks good. And I'll just say, for those that are having trouble, you really want to parse this out into 3 steps. There's kind of step 1, which is right here. So when I'm grading these things, just so you know, I'm kind of looking for 3 things. One is the induction, was the induction hypothesis stated clearly? And that looks great here. So that is stated clearly. No issues with that. Okay, part 2 is to state what it is that you're trying to prove. This really helps the reader understand what you're trying to do. And so here we want to show this property holds when n is bigger than k, let n equals k plus 1. So this would be kind of step 2. And that looks good. And then all of this is step 3, the proof. So just so you guys know, on the homework, these problems were graded out of 6 points, the induction. So you would get like 1 point for doing the base case, 1 point for setting up the induction hypothesis, and then step 3 would be like the bulk of the points. So all of that looks good. And actually this proof is quite good. Does anyone see a problem? There is a big problem with this, however. And don't be afraid here to critique each other. That's what we do with proof writing. So there's nothing personal here. This is actually really great proof. There's one critical mistake that apparently is subtle because I don't think others are picking up on this. And I've been seeing this mistake, and it actually is quite a big mistake. Okay, we don't have that, right? We assumed it's true for things less than n. So if n is equal to k plus 1, I don't know that's true, right? That's what we're trying to show. So resist that temptation of writing this out. And if this student just skipped that and instead said, we start with this, that equals that, and all of the rest of the calculus is correct here. But this thing that you're trying to prove, we should just ignore it and just know that's where we're trying to head to. So that's what was proven over here. So that's a check. So this is a really good proof. That gets a 5.5 out of 6. And again, like the feedback here would be that base case is a little bit confusing to follow, and just do not write out this, that we have this fact when that's the thing that we want to prove. So I think on that homework assignment that you did last time, that was the error in that induction proof that you were given, is they did the same exact thing in that one. Okay, any questions about comments on this one? So for the person who did this proof, yeah, I'm great job on this proof. I just think that you, these are good things to point out, just so you know what I'm looking for when I'm reading these. Okay, so let's get to the topic for today, which is dealing with Cartesian products. So if it's helpful, I can just chat in this. This is on Canvas too, but if you don't have this PDF handy, I'm trying. Oh, that does work. I just chatted it to you all. Okay, so when we talk about the Cartesian product of two sets, it is just an ordered pair, right? So the first thing in the pair comes from the first set. The second thing has to be an element from the second set. And so these could be, the elements could be numbers, they could be letters, they can be colors, right? Elements of sets can be anything. So don't assume that we're working with numbers. But we could talk about kind of discrete sets of things like the set 1, 2, and the set X, Y, Z, in which case we just have like a finite list of things in the Cartesian product, or we can deal with continuous ranges of values. So here, this is indicating the set of all numbers between 1 and 2. Let's see. Sorry, there's a bit of a delay again. Can you guys hear me? Yeah, okay.
Yes.
Yeah, I can hear you.
Okay, that's a little bit better. Okay, I think we're back on real time. So yeah, so this is consisting of all of the numbers between 0 and 2. This is all of the numbers between 1 and 3, right? Not integers, but all of the real numbers in here. So typically we represent ordered pairs of numbers, right? In, I'll just say, right, this would be a subset of R cross R. So usually we represent these in like the XY plane. So I can think of the first one. Well, I guess I would not put 0 over there. I could think of the first one as going from 0 to 2. And then this one going from 1 up to 3. And then this set would be all of the things in here, right? All of the points that have an X coordinate between 0 and 2 and a Y coordinate between 1 and 3. And this is a solid region which lives inside of the Cartesian plane. And I'll just say we oftentimes write that as R2, even though it's not like R squared. Okay, any questions? Okay, so let's think about a couple of examples. And yeah, so this one over here, we're on the reading quiz, I believe. So what do you guys think about 4? You think that was true or false? You can chat it in or speak up, whatever you guys prefer.
I said true.
So we have to vote for true. So if we want to prove these things or disprove them, right? Just remember for subset, to prove something is a subset of another set, if it's true, then what we need to show is if we have something in the first set, then it follows that this is in the second set. So this needs to be true for all X in the real numbers. And if it's false, then we just need to give one counter example. And in this case, a counter example would be something that occurs in R but doesn't occur in R cross R. Does anyone think of a counter example? So this is actually false statement over here. So some people are saying, like, I'm getting some private chats at least, that this is false because that's what the quiz said. True. But let's prove this with a counter example. What's somebody's favorite real number? 1.
4.
Okay, 1 or 4, those are great choices. So we'll take 4. Right, 4 is in the real numbers, but 4 is not in R cross R, right? R cross R are points in R2. So these are ordered pairs. So this is not included in there. So R is not going to be a subset of R cross R. Keep in mind, these are points and these are numbers. So they're kind of different things, right? It's kind of apples to oranges here. Any questions? Kind of disproving these statements just involves giving one counter example. The ones that are true, we'll have to prove them a little more formally. And when we're dealing with these proofs today, I don't think we're going to get any induction. We're going to have to think back to direct proof, contrapositive, contradiction, those proofs.
Wait, I have a question. So
Yeah,
four
sure.
belongs as a real number, but it doesn't belong to R cross R because it's not a coordinate.
Yeah, so R cross
Not
R means you have a pair of numbers. Yeah, so
Oh, okay.
you have like a point X, Y. So 4 is just one number. R cross R would be a pair of numbers. So that's why 4 doesn't sit in R cross R.
Okay, sorry.
Yeah, no problem. Okay.
Is that why?
Yeah, go ahead.
Is that why natural by natural? Is that why natural by natural was a subset of real by real, but
That's right.
this opposite would not be true?
Yeah, that's right. So when we're thinking about this cross this, that is a subset of R cross R. And again, here you could say, take any ordered pair X, Y, which is, I'll just not do a big formal proof, but if we took any number X, Y, which is an N cross N, right? This would mean X is in N, Y is in N, and so that would tell us X is in R and Y is in R, and therefore X, Y is in R cross R. Would be the gist of that one. Yeah. Okay. A cross B equal to B cross A. Let's see. Let me get a poll. So question here is, do you believe this? Did you think this was true or false? And so you can just give me a yes or no. The fact about the explanation, we don't have an explanation yet. So I'm just curious whether you guys think that, yeah, this is yes, or this is no. Oh, okay, that was pretty quick. Okay, so here we're getting, I'll end it there since we seem to have overwhelming agreement that this is wrong. And so if we want to prove this is wrong, we can give a counterexample. Right, so we can just pick, again, when you're doing counterexamples, you typically want to do something easy. So let me just let A be the set 1, 2, and B be the set 3, right? Then we would have something like 1, 3 is in A cross B, but 1, 3 is not an element of B cross A. And so if they don't share all of the same elements, then they can't be equal to each other. Okay, any questions so far? Okay, then let's try 3 together, and then I'll give you guys a chance to try 5. So last time we did a complicated one together, and you guys had one that was maybe a little bit easier. Today we'll flip it around. So I'll try doing this one. Should be a little bit easier than the next one, but they should be pretty similar. So here we've got a conditional statement. So we've got an if-then statement. So let's try and prove this. So this is true. So here's my suggested start. And so based on this, what proof technique am I trying to do here?
Direct.
Yeah, so we're going to start by assuming P is true, and then we're going to try and show that Q is true. Without kind of going too far, sorry. So without like thinking ahead too far, usually direct proof is a good place to start. That's the nicest proof, I would say. Don't see how induction would come into play here, right? We're not really thinking about anything as n is getting larger. Okay, and so if I want to show this, let me just write this out. Let me just call it XY, that for any ordered pair XY in A cross C, that this has to be in C cross D. Right, since again, that's what needs to be shown if we want to prove subset. Sorry, I messed something up. This should be a B cross D, right? So how do you think this is going to follow here? So what would I need to show in order to conclude that XY is in B cross D?
That X is in B and Y is in D.
Yep, thank you. That's right. So as long as I know that this is inside of B and this is inside of D, then this ordered pair is going to be in the Cartesian product. And hopefully you see, okay, if we assume this, I know that X is in A, and if X is in A, that means it has to be in B. And that's kind of the key here. And then that's going to give me that X is in B. Next, this is telling me that Y is in C, which therefore implies that it's in D. And that would give it to us. So let's kind of just write that out. So let's consider some arbitrary element XY in A cross C. And so kind of one thing that you should keep in mind when you're trying to write these proofs that I kind of catch from time to time is that this should kind of be a flow of logical arguments. So, you know, this sentence should follow from whatever might have just been claimed here and so on. So these should kind of move through the proof in each sentence is kind of connected to the previous one. So if X, Y is in A cross C, then we know X is in A and Y is in C. And so now this is going to tell us that X has to be in B. And rather just say like, therefore X is in B, it might be nice to just clarify how we know that X is in B. And that follows from the fact that A is a subset of B. And similarly, since C is a subset of D and Y is in C, we know that y is going to have to be in D. And this is what tells me this ordered pair is in B cross D. Okay, and so here I've left nothing for the reader to really think about here, right? And we've made this abundantly clear. And so, you know, some things that I'm catching when I'm reading proofs are kind of leaving out some of these things over here, and just saying, okay, I know X is in B, Y is in C, so we have this. I'm not necessarily taking off for that, but I do think it's doesn't not asking a whole lot of work just to kind of make sure that you justify how we got this. So this just kind of connects all of those thoughts. And once I've shown that any element of A cross C is in B cross D, this tells us that A cross C is a subset of B cross D. Any questions? Okay.
I have a quick question.
Yeah, sure.
Wait, is it A cross B and then C cross D, or you have A cross C and then is a subset of B cross D?
Yeah, that's what we wanted to show, right?
Oh, never mind. I'm blanking. Okay.
Yes. These things were ordered in this way. Yeah. Okay, so I'm going to break this up into two groups, and I'll have Lindsay kind of manage one, and I'll try and manage the other group. But the idea here is to try and prove 5. And just as a refresher, if I want to prove that set P is equal to set Q, then we need to show X in P implies X in Q, and we also need to show X in Q implies X in P. So we need to show, this would tell me that P is a subset of Q. This tells me that Q is a subset of P. Once I prove both of those things, that then proves P is equal to Q. So just a little review of set equality, how we prove set equality. So yeah, so let's give this one a shot. You might want to give yourself some space, and we'll see how this one goes. But any questions before I break us up? All right. Rooms are open. All right. Welcome back, everybody. So how did things go in the other breakout room? How far did you guys get through your proof?
We got to the second. Yeah.
Say that again, Giselle. Sorry.
Oh, I don't know. Yeah, sorry. I was gonna someone already said it, but we were on the reverse. Because we
Okay.
were trying to prove one's a subset of the other, so we were on the second half.
Got it. Okay. Yeah, let me share what I took a screenshot of the whiteboard that we had. Just pasted it over here. I'm so sorry, I can't edit this because this is a screenshot. But kind of just to kind of read through this quickly. So we've got A, B, C, and D sets. So the forward direction would be, we assume we have something in the set on the left, right? Which would be in A intersect C cross B intersect D. And we want to show that it's in the set on the right. And so right, this follows from like X is in A and we know X is in C, Y is in B, and Y is in D. So that tells us that XY is in AB and XY is in CD. So therefore it's an element on the right side. Just a quick summary of that one. And so did you guys go about in the other room, the forward direction in a pretty similar way, or was there something different that you guys did?
It was pretty similar.
Okay, thank you. Okay, and then because we want to prove equality, then we would take an element in the set on the right side, which is A cross B intersects C cross D, and we want to show that it's going to be in the set that was on the left side. So for this one, it works pretty similarly as the other direction. It's almost like we just flip it around, but now we start with something which is in this set, A cross B and C cross D. So I know that XY is in A cross B, and it also has to be in C cross D. So if XY is in A cross B, it's an element of A, and Y has to be an element of B, right? That's what it means by definition for Cartesian product. And we also know that X is in C and Y is in D. So from that, we know X is in A and X is in C, Y is in D, and Y is in C, and that gives us XY in the set on the left side. And we were kind of talking, so if you kind of are reading this, I took a picture while they were in mid-writing. So sorry, they were kind of writing over here and I took a picture, but this was trying to say, like when you end this first direction, it would be nice to say like, okay, this proves that the left side is a subset of the right side. And then it might be nice down here to just say like, what did we just do in this direction? We proved that the right side is a subset of the left side. So thus these two sets are equal. Okay, any questions or thoughts about that one? Okay, so I will leave the next couple of ones on this worksheet for you guys to have something to think about, practice at home. I think we did the trickiest one out of it. So there are two other ones, 6 and 7. So 7 has like a triple. What just happened here? Yeah, so these are the two remaining ones. So I think these would be good to practice. But any last questions about this before we take a look at the next? We'll start working on the next worksheet. Okay, so next up, let's take a look at this worksheet on 16, which deals with relations. And I can chat this in if you don't have it handy. Okay, so we have a kind of probably an informal idea of what it means for a relation. We're just defining like how two things are related to each other. So, you know, here's a relation. And inequality is a relation. This is a relation. So we have all sorts of things that we could say are relations. So keep in mind, we're going to define relations using a set theoretic definition. but our sets are not restricted to just being sets of numbers. So these can be sets of anything. And so these are going to be true, false things. So either two things, two elements are going to be related to each other, or they're not. So let me just kind of say how the textbook does it. If you're reading along there, in 11.1, they just define a relation on one set. But we can also define relations from one set to another. So this is done later, but we might as well just think about these at the same time. So that's the more general definition, which is later in the section. So if we have two different sets, then a relation from set A to set B, we usually denote that with an R, would just be a subset of the Cartesian product. And so if we talk about a relation from a set to itself, then both of the sets are just A. So for example, so again, a relation would just be, here's a set A, here's a set B. Anything that is a subset of A cross B, we can consider a relation on A cross B. So there are tons of different relations that we can define between these sets. So the notation that we use to describe whether or not two elements are related to each other is X, R, Y. So this is saying really X is related to Y. Okay, which means XY, I have a mild delay here, it means that XY is an element in the relation. So to think about these sorts of things like, are these true or false? Is 1 related to 3? Using this example up here, and really what this is asking is 1, 3 an element of R? And here it is. So this would be true. So what do you guys think about 1, 7?
Is this asking specific about the relationship that's predefined or a relation that could be defined?
Yeah, so we're talking specifically about this relation R up here. I'm getting some comments, but maybe let's open this up. So what do you think? We're talking about B here. Do you think that this is true or false? 1 related to 7, as defined by the example of 3. Okay, so here are the results. So we had a lot of people saying false, but people were a little hesitant about that, or at least not totally convinced. Right, and so the idea is, given A and B, there are many different relations that we can define from A to B, right? And so it's not like given a set, there's one unique relation between them. There are tons of different relations. So here's one of them. So anything that's a subset of A cross B would be considered a relation between A to B. So if 1 is related to 7, that would mean 1, 7 would have to be in this set R. And here we can see that 1, 7 is not a coordinate in this Cartesian product. So this is false. Since 1, 7 is not an element in R. Questions about that? So let's try this again. Same question on 3. So now 3 is saying, is it true that 3 is not related to 3? Okay, thanks for these. Let's share the results here. So here people were a little more confident. That's good. And this is indeed true. So the idea is this is going to be true if 3, 3 is not an element of R, right? It's going to be false if 3, 3 is an element of R. Since if 3, 3 is in R, that would imply 3 is related to R. And so we look at the pairs in example 3. 3, 3 is indeed not inside of that set. So this is true since 3, 3 is not in R.
Hey Adam, can you clarify something?
Sure.
I don't think I understand the difference between B and C. Because if 1, 7 is not in R and that is false, why is the right side the true one?
This has a little slash through the R if it's not clear.
Oh,
So,
sorry.
that means
Yeah.
3 is not related to R. Yeah, sorry. That might have been small, but yeah, there is a little cross through them. So we use this kind of same thing of like putting a slash through something to say it's not related or it's not in the set. Yeah.
Gotcha. Sweet.
Okay, so here are a couple of examples of different relations that we could have. Again, so any two sets we can get some relation. So we can let S be the set of all students at CU Denver, and let C be all of the courses offered at CU Denver. And then we define relation E to be enrolled between these two to say that student X is related to course Y if student X is in course Y. So for example, just to pick on Keenan, we would say Keenan is related to Math 3000 because he is enrolled in Math 3000. Okay, so these can be more abstract things is the point. But here, in this example, there was really not a rule that I can see for when is an element in A related to an element of B. We kind of just arbitrarily seem to have written out a set of ordered pairs and said that's our relation. When we start to think about functions, which we will do as special relations, we typically think about like what is the rule for this thing being related to that rather than writing out all of the pairs. So that's what's going on in example 4. Clearly, we wouldn't want to write out that set. That would be a really large set. So we could just describe it with a rule instead. So for any sets A and B, as you might be thinking, the total relation would mean that every ordered pair AB is in the relation. So basically that's the largest possible relation that you can define. So this is saying any element X in A is related to every element Y in B. So the total relation so in that case, the relation is just the entire set A cross B. And the other extreme would be that all X in A are not related to any Y in B. In which case, the relation here is the empty set, right? That would contain no elements in there. So those are kind of the extremes. And in between, we have all of the different subsets of A cross B that could be a relation. We'll kind of come back to example 6 in a sec. Any questions so far? And so kind of just where we're heading on this is eventually looking at very special relations that have certain properties like symmetric, reflexive, transitive properties that will kind of define special relations between these sets. Also we'll take a look at special relations that are functions. We've talked about that a little bit. This example over here would actually not be a function because the number 1 is mapped to 2 and it's mapped to 3. So for a function, we would just want to have each input gets only one output. But we can frame functions in this relation setting as well. Okay, so let's think about 1 and 2. Using these empty and total relations, again, that we have up here. So here's poll again. Let's get everybody sharing their thoughts. So what about the first one? Do you think that statement is true or false? Okay, let's see where everybody is at on this one. So things are a little divided here. So there are a couple of things that we need to check. So first of all, since we're defining this relation, we're calling it P. P is going to be some subset of Z cross Z. So the first thing we want to check is, right, each of these things should be an integer, which they are. But the empty relation tells us that each element in A, so each integer, is not related to any other integer. So when we define the empty relation, P is just going to be the empty set. So this is a false statement here, since nothing is related to anything by P. Since kind of by definition, the empty relation is saying any integer is not related to any other integer. So whatever numbers I put there, that would be false. So any questions, since I think there was a little bit of confusion there. Even saying one is related to itself is something, right? So we want to rule out that possibility too. Okay, let's try question 2 out. I wish I had Jeopardy music, would be perfect for these polls. Okay, I think we got them all in here. Thanks for that. So everybody seems to some extent, feel convinced that this is true. And this is true. Really, the only thing we want to make sure is that these numbers 3 and 7 are elements of R. As long as they are, then anything in R is related to anything else in R. So here we've got 3 in R, and we've got 7 in R. And so the total relation says anything in R is related to anything else in R. Okay, so just to kind of look ahead, we would call this a reflexive property for this relation. Not all relations have satisfy that property. Okay, any questions? Okay, good. So let's take a look at the last one here that we kind of didn't talk about yet. So this is this nearness relation. Let me paste it down here. That's what the, oh, there is a delay here. Sorry, there you go. So that's what the nearness relation is saying. So this is like a topology type of result here for anyone that's kind of curious about what field of mathematics this would be in. And so how you can think about this is you pick some number x, y. And sorry, so here we're actually just in R1 here. We're defining this relation on R. So you're kind of going epsilon below x, epsilon above x, and for any values that are inside this open interval, we would say x is related to y. Okay, and if y falls outside of that region, then it's not related to y by this property. So over here, we've got our first number, which is pi. Happy belated Pi Day, by the way, to everybody. Sorry. Let's see. Does anyone have a calculator handy? Maybe I do. Might be useful to write this 22/7 as a decimal. So I'm getting 3.1428. I'm rounding things off over here, but the idea is, right, if our nearness relation is by 0.01, then we're going to go up and down by 0.01. And then we want to think about, is this second number inside that interval? So let's see, last poll for the day. What do you guys think about this? Is pi related to 22/7 by this nearness relation? Was that Jeopardy music someone was piping in here?
Yeah.
Thank you. All right, take another 10 seconds if you're still thinking about it. Okay, maybe I should give you guys some money and we can make this a true Jeopardy challenge here. All right, so most people were thinking yes, we had some not so sures, but again, all we want to do is make sure if y is in there. And here's our value for y, and this does fit, and it's somewhere between between pi and 3.15. So this is true. Okay. So yeah, I'll kind of leave these. We can pick up with thinking about 4 and 5, and so we'll start to move on and talk about properties of relations next time. So that's what the reading quiz will be about, like transitive, reflexive, symmetric properties. And so just so you guys know, you know, I'm not planning to shift the exam. I think we're fine. I built in some a cushion there in case something happened. So the exam is going to cover everything up to and including what we cover next week. And then, so the exam was originally scheduled for Wednesday, what is it, April, excuse, 7th, is that right? I'm trying to remember the date. Yeah, so that was April 7th. So just so you guys know, the plan is next week we'll wrap up the material. We'll have Monday, April 5th to review for the exam, and then we'll have the exam on the 7th. So that hasn't been thrown off from the original plan. Okay, well, have a nice afternoon, everybody. Yeah, the induction homework is due Monday, not today. We moved that back. I will let you guys know once I get these assignments graded, and it might be helpful to just look at my comments on homework 6 before you submit your final work on homework 7. Okay, have a nice afternoon, everyone.